But there's no rail runner station.
Well, we can, no, we can, you don't need to take that. I kept, that's what I've been saying. Yeah.
Want me to take it out a second?
So that was 3 minutes.
So I'm keeping rail runner in.
Yeah. Because we can detect no line of
Okay, so all sensing is rangefinder, then we go odometry to servo, delay to moving. Moving is the U-turn. Move forward is this, and then wheel odometry. Back is our follow line, that's now at the U-turn.
Then you detect no line.
The thing is that, okay, so then we go to top. Well, they have to kind of be driving already. Whatever, for the purpose of and then when we detect the line again, no. So then it's going to be odometry?
No, you just have constant detection. Because
what would trigger us to go from rail runner to know that we're back on the floor? So from driving those,
there wouldn't be like really a transition. The warp wall transition would be. That would just be the warp wall is just line following until there's no line.
But if I go from my drive top rail runner to 20-yard jack, what's that set?
That would be line following until there's no line.
Okay, so rail runner is not going to go to, it is going to go to.
Yeah. It goes back to forward.
Because?
Yeah.
What's the
Just a delay. Like a delay. Or wheel odometry or delay. But some sort of timing so you can figure, oh, it's gotten all the way across. And say like, okay, now it's
follow line, we go to opening jack.
No line detection. Yeah. And that's kind of how that
The no line detection, should I change that?
That's not specifically.
Kind of what we need to, I had it printed and ready.
Maybe he's taking it.
Okay, let's get started. So, as I said on Monday, what we will do today is to spend some time to go over the solution for homework 3. The way I'm going to do this is to make sure that we don't spend too much time on this. So thinking we go over. So what I will do is basically ask you guys to nominate. Then I will go over the details. That being said, okay, who want to nominate a problem for us to discuss? 16. Yes. Okay, 16. Find all departments that offer number courses between the departments similar to example using Winter Olympics as example. For each country that has won the same number of medals, show the country with the least number of athletes. Why? Because that's the most effective country, right? Or in our example, that's the most effective. First of all, you need the professor table shows you which professor works for which department. Obviously, you need that information to count the number of professors in the department. Okay? You also need the session table because the session table tells you which course is being offered by which department at which session. So first of all, you need to identify these two tables to construct your query from. You do a join between them using department name, obviously. You want to make sure you talk about the same when you count join condition. Then you group by, obviously it should be done with respect to department, right? Because with respect to either the number of professors or the number of courses, it's an aggregation over a department. So obviously you should do group by over department name. So far, I think quite straightforward, right? And you count distinct number of course number. Here you want to use distinct because the same course may be offered multiple, and you count the distinct number of professor names. Okay? Which basically what this gives you is number of courses and number of professors from a given department. Okay? So far, it's just a standard group by aggregation query. You should have no trouble in doing that. The tricky part is, how do I return only those departments that have the least number of professors and do so in comparison to other departments that offer the same number of courses? That's the real challenge. So obviously you need to have a hiding condition because you're doing this check at group level for each department, that the number of professors, which is the same as this, must be the smallest. If you're the smallest, which implies that this must be true. This value, this count of number of professors must be less than or equal to all such count from all departments having, so basically I duplicate this structure from the outer block in this inner block and enforce that the number of courses must equal to the number of courses from the department from the outer block. Okay, that's it. So what the inner block does is find the number of professors for each department who offer the same number of courses as the current department you're checking from the outer block. That's it. All right, any questions on this?
On the end, it says that sanitary engineering has one course, but the database.
Yeah, so I'm prepared for that. Remember, the question asks you to find the department who offer those courses, right? So in the database, we actually have two tables. One, we have a course table which shows which course is associated with which department, but that course may not be offered. So you want it's really straightforward. Okay, one problem done. 3 more to go. Any other recommendations I should go over? Oh, this is the belly of the beast. Once we are done with this one, we're done.
So I have a question on number 7.
Number 7. Okay, let's go over number 7.
So your solution there has the number of courses as 0. And there was a discussion post that asked about whether you should consider students that did not take any courses or use it.
Okay, I see what you're saying. Okay, either if you ignore those students without, but this is different, right? This is talking about the courses a student taken. The discussion is with respect to a student without major, right? This is different.
No, the discussion was about students that had not taken any courses.
Ah, then fine. Then you can, if you also return those with taking one course, that's fine. But the right way to do this is to use left outer join to find out those who have taken no course at all. Then if you do an aggregation over that, you will get count 0 for 2 students. But that being said, if I said that in discussion board, which I take your word for, then returning those students taking one course is fine. Meaning that you're not doing a left outer join. You're doing a join between the two. Does that make sense? Okay, cool. Okay.
So
same problem or different problem?
different.
Different. Which one?
For number 9, like, do we still need to construct an empty table, or we just set empty set?
Say again.
So, do we still need to construct an empty table?
You mean the results here? Well, if you just show, if you say something in the nature of this is empty, that's fine.
Like an empty set.
Yeah.
Okay.
Okay. Any other questions? Go ahead.
I noticed for like 14 and 15, you have
14 and 15.
yeah.
Okay.
So on the answers, you have like an extra thing. So on the 15, for example, it says find a department with more than 5 students. But
Is this column really needed? No,
Yeah.
that's not needed. But I include this column just to make the answer more comprehensible.
For problem 2.
For problem 2,
Just
okay.
any of them.
Assertions.
Yes.
Or constraint checking. Yes.
You can do a check right after the variable, like it says salary float check.
Yes. If it's a column constraint, you can do that. If it's a column constraint, you can do that. Any more SQL questions? If not, I will take that as you guys are ready for the SQL queries to write for your midterm, right?
So it's like you said, if we can do all these easily, we should have no trouble on the midterm, right?
Oh, if you can do 16 easily, yes, you can sail through midterm without any problem. Honestly, you can come to midterm, have a good time, and be done with it. And speaking of midterm, I made an announcement right on Monday as well, specifying what the open book policy is. In particular, pay attention to the requirement. Right, the requirement is you have access to really 3 things and 3 things only: lecture slides from Canvas, homeworks and homework solution on Canvas, not your own homework solution. That's not allowed. What's the other thing I said? Quiz. The solution to the quiz, right? So those are the 3 things, and only those 3 things you have access to. You cannot make reference to textbook. You cannot make reference to any notes of any nature. For example, if you decide to bring a printed copy of the lecture slides, then there should be no note of any kind on that printout. if you do decide to access those items electronically, then make sure you are accessing the copy that you download from Canvas and without adding any personal note to it. You may wonder why I do this. The reason for this is to make sure we have a level play for all of you who participate in the midterm. Some of you like to take a lot of notes. Some of you like, and I hate when professors say, oh, you can bring a cheat sheet or 1 page to the exam. Because if I have 1 page, I write down maybe, I don't know, 10 items. The person sitting next to me can write down, I don't know, 100 to 200 items using really small font. That's not fair. Not fair at all. Okay? So the simplest way to prevent that from happening is, do not allow any notes. Okay? So that the point is, from an information theory point of view, you guys have access to same number of bits. Nobody has access to a single bit more or a single bit less. Okay? And another thing I'd like to clarify, the open book policy is a privilege. It's not a right. Just like driving is a privilege, it's not a right. So do not come back to me, oh, this is unreasonable. I should be able to do this, I should be able to do that. No. It's a privilege, it's not a right. Okay? So it's not open for negotiation. Okay? It is what it is. Okay? But that being said, the open book policy, in my opinion, is already very generous because the midterm problems are going to be the same type of problem we have already seen from homework and quiz. Okay? If you have access to homework solutions and quiz, and that should help you a lot in solving midterm. But that being said, you do want to do your revision before taking the midterm. If I were you, I would not rely on, doing no revision whatsoever and coming to the midterm and relying on making reference to the homework and quiz solution on the spot and trying to figure out, oh, this is why I'm doing this. If you do that, you might run out of time. Because it should take you maybe 3, 4, 5 minutes to write an SQL query. If you try to understand the solution on the fly, on the spot, it may take you 10, 15 minutes to just understand the solution. Then another, 5 minutes for you to construct your own solution. That will take too long. It will not work like that. Okay?
Can we compile the allowed information any way we choose? Like,
say again?
You said we could print out the lecture
yeah.
slides.
Yes, you can.
So we can assemble them, because I'm interested in pulling out the interesting stuff to me and weeding out the stuff.
What do you mean by assemble? Define assemble.
Put interesting slides in their own PowerPoint.
No.
Okay, so it's literally just the file.
Literally the file as it is, yes. Because once you do that, there's no way for me to check. I don't want to spend 5 minutes to check. Everyone brings some material that's same to what's there. Once you assemble it, how do I verify is a subset of what we have? How do I verify that? It will take a lot of time for me to verify that if everyone starts doing that. Does that make sense? But if it's the same material, I can easily just sample a few pages and look at it if I want to.
Okay.
Does that make sense?
Yeah.
I would say, the easiest thing is to do this electronically. Right? Bring your laptop. What's more effective than Control F?
Yes.
Keyword search.
No,
Or graph. You know what graph is. Right? What you are trying to do, what Justina was proposing just now, is to build a hash table of some sort, right? To be more effective in accessing information she wants. That's a hash table. But if I give you laptop and access those material electronically, what's more effective than Control F? That's like hash table, right? So I think if I were you, I would just do that. Okay, all right. Any other question you want me to go over? So we've been talking about SQL for the most part. Let me spend maybe 1 or 2 minutes to go over one of the constraint checking problems. So this has been extensively discussed on Canvas, right, on the discussion board. the point is the following, right? You can, in practice, you can do constraint checking using one of the following three methods. One is, do not enforce any constraint in your database. Rather, enforce those constraints at your application level code. In other words, in Java, in PHP, in JSP, in Ruby, in Python, in C, in C++, whatever language you are using in writing your application level logic. You can always check constraint over there. Anyone who tries to insert a new record through your application interface, you can check that. Of course, the downside of that, what's the downside of that? The downside of that approach is if somebody managed to bypass your application level code. For example, somebody hacked into your backend database system directly without going through the interface you have, then you have no defense against those kind of attacks. Does that make sense? Because you have no constraint checking in your database level, in your database engine. Right? So that's option number one. Option number two is to enforce those constraints as the database level, meaning that in my application level code, I do nothing. And when it comes to my database, I will have constraint checking in place, either through assertion, which is what we're doing here, or using trigger. Trigger, in practice, typically, trigger is much more involved to write, because in order to write a trigger, typically you need to understand a language called PL/SQL, which I talk about in our lecture briefly. And the syntax of PL/SQL varies a little bit from one commercial database engine to another commercial database engine. So it doesn't carry over. Right? So there is a little bit of learning curve there. However, it's really powerful and really flexible. Assertion, on the other hand, is a quick and simple fix to many of the constraint checking issues you may have, like we demonstrated here. But the downside is, because it's not as flexible as trigger, it becomes expensive to enforce for a database engine if you have many assertions. As a result of that, many database engines by default disable the support of assertion checking. So if you are the database administrator of your database engine, you can, of course, enable the check of assertion again. But if you're not DBA, you have no access right to enable that. Then assertion is not even an option for you. The same goes to foreign key reference integrated constraint checking. You might have noticed that in your phase 2 development, for example, MySQL by default disable not only assertion but also foreign key reference integrated constraint checking. Okay, so for performance reasons. So that being said, I think for you guys, it's still useful to know both assertion and trigger. Knowing both will be useful moving forward now. Right? So in our homework, we decide to go with assertion, but if you choose to do this using trigger, that's totally fine. Well, either way is fine. If you choose to go with assertion, let's look at one example, right? Like no employees every employee's total percentage of work time should add up to 100%. Okay. How do we enforce this? Well, the trick for most assertion checking is to construct a Boolean statement. So, for example, in this case, you're using the keyword check followed by the SQL keyword not exists. Remember, not exists followed by Marta set A. Check the following. Check if A is empty set, then this returns true. Otherwise, this returns false. Right? We talked about this, right? So in our case, what is this set A? Well, you basically construct this as employees whose total percent time adds up not equal to 100%. You find those employees whose total percent time add up not equal to 100%. And if this is an empty set, that means the constraint is being enforced. Does that make sense? So that's kind of the logic here. And you task then reduce to how to write this in SQL. How to write this in SQL? Oh, that's easy. That's just a simple group by having clause. And you can do that. Okay? And other assertion checking, many other assertion checkings can be reduced to something similar to this. Can be reduced to something similar to this. Okay? So that's kind of logic here. Any other question on homework 3 before I move back to our lecture on functional dependency and normalization? No? Okay. So on next Wednesday for the midterm, we start at 11:50. We'll go all the way to, I will overrun for 10 minutes to make the test 90 minutes test. Okay? All right. So let's go back to So last lecture we talked about BCNF, right? Remember? Just to give you a quick recap what BCNF is. BCNF basically says the only constraint you have, the only functional dependencies you have is a key constraint. Other than, of course, trivial functional dependencies. Other than trivial functional dependencies, the only constraint that you will have for your schema is a key constraint. If that's the case, then the schema is in BCNF. We also argued why this definition makes sense, because when you follow this definition, you end up with no redundancy whatsoever. You have no redundancy in your schema. In other words, from an information theory point of view, every single bit in your table is needed. Every single bit in your table is needed. When this is violated, that's not true. For example, using the simple example, if you have a functional dependency x determining A, obviously this has violated the BCNF requirement because x is not a key. X is not a key, and this is not a trivial functional dependency. If that's the case for this table, you know this value is A, then the bits representing these two values are redundant. Those bits representing those two values are redundant. Okay? So that's the purpose of BCNF. It's a very simple definition, actually, if you think about it. Right? The next question is, how do we enforce BCNF? In other words, given a set of schemas, how do I make sure I have only BCNF schemas? I have only BCNF schemas. And this is not trivial, unfortunately. We used the example to demonstrate this. For example, you have a table ABC like this. You have A determine B and C determine B. Both of these functional dependencies have violated the BCNF requirement. Right? Why? From A determine B and C determine B, you know that A is not a key and C is not a key. None of the two attributes is a key. So A is not a key, C is not a key. As a result of that, neither A determine B nor C determine B satisfies the BCNF requirement, which says you can only have key constraints. You follow that? So that's a simple check. So this is not in BCNF. So the solution naturally is to decompose the input schema into two smaller schemas. One option is to decompose them into AB and BC. But if you do this, if you join them back, you do not get the original relation back. So you have a problem. Nevertheless, it's worth noting that in this case, the two relations you have, AB and BC, they are actually in BCNF. Why? The only dependency, the only dependency that holds over AB so the only functional dependency that hold over here, I will denote that as F1, the set of functional dependency hold over this. Is A determine B, and the set of functional dependency hold over this is C determine B. Right? Now, with respect to this new schema, clearly attribute A now is the key. Why? Because A determine B, and there is a trivial function dependency A determine A. Henceforth, A must be the key for this schema. Similarly, does that make sense? Yeah? So because of that, both of these are BCNF schemas. Both of these are BCNF schemas. So you are fine. However, the problem is when you join them back, unfortunately, it doesn't give you the original instance back, ABC. So that's the problem. And that's the problem. Naturally, this leads to a question, which is, do we have a decomposition method that leads to the following. One, BCNF schemas. And second, no loss of information. So this decomposition satisfies condition number 1, but does not satisfy condition number 2. By the way, the loss here doesn't mean losing some bits. Loss here can mean that gaining some bits that's not there. The loss is defined both ways. We define loss as long as you do not get the original instance back, we consider that as a loss. Okay? Sometimes more is not a good thing. More is also a bad thing. And you want to be exact. Either less or more is not good thing. So in our context, less number of records or more records after joining them back, both are considered as a loss of information. Okay? So do I have a solution for this? So formally to define this no loss of information, we formally define this. Here is the formal definition. We define this concept of lossless join decomposition. What it says is if you have a schema R, you decompose that into X and Y, where X and Y are two subsets of attributes from the schema of R. Two subsets of schema from R. So in our example, this is your R. In our example, this is R. This is X, and this is Y. You follow this? Okay. Lossless join decompositions require that projection of X, okay, given an instance from this, from this schema R, then projection of this join with projection of Y of R must equal to R. And actually this must be true for any instance. For any instance. That this must be true. For any instance, this must be true. Okay? Do you follow this? This is the definition of lossless join decomposition. So how do we make sure we have lossless join decomposition? How do we do this effectively? There is this very effective method we're going to introduce. I'm not going to show you the proof of this because the proof of this is non-trivial. It's not trivial at all, actually. But I'm going to introduce this as a fact, and you can take this and use this as a tool for your decomposition. And when you do this, you can make sure that whatever you do, your decomposition is guaranteed to be lossless. So how do we do this? Well, the idea is the idea is as follows. So you have a schema R. Okay, you have a schema R. And I'm going to decompose this into X and Y. So I'm going to decompose this into two smaller relations, R1 and R2, where my R1 is X, my R2 is Y. You follow this? X and Y are subsets of attributes from R. Of course, and also the requirement is X union Y must equal to R, meaning that you're not losing any attribute in the process of it. First again. Now, the claim is this is lossless if and only if. If and only if means that it's both a sufficient and necessary condition. Do all of you know the difference between sufficient and the necessary conditions? How many of you know what's a sufficient condition? What is a sufficient condition? What's a sufficient condition?
Wouldn't sufficient be if then? Simple like that.
Sufficient means that if that condition is true, then your claim will be true. Can you give me an example of a sufficient condition?
If I do well in the exam, then I do well.
Say again?
I claim that if I do well in the exam, then I have a good grade.
Yes, if you do well in the exam, you have a good grade for you study in this university. That's a sufficient condition. Okay, what's a necessary condition? Necessary. Necessary condition is the only if part, right?
It's just if not A, then not B.
If not A, then not B. Yes. Can you give a specific example of that?
Okay, following the same example. If you don't do well in the test, then you won't do well.
Not really. I mean, the way to interpret what you said, following the same example, the necessary condition should be stated the following. If you do have nice grade, then you must have done well in your test. It goes the other way. You may wonder, wait a minute, are the two equivalent? In this case, yes. That's because doing well in exam is both a sufficient and necessary condition for having nice grade. Why? Because grade is computed directly from the score of your exam. Can someone give me an example where it is a sufficient condition but not a necessary condition?
If you had a big extra credit assignment, then doing the extra credit assignment would be sufficient but not necessary condition.
Say, can you repeat that again? If you have a
if there's an extra credit assignment for the class,
okay.
then doing the extra credit assignment could be a sufficient but not necessary condition.
For
passing the class.
For passing the class. I see the connection you're trying to make, but it's rather weak because for passing the depending on how we define passing the class, that makes sense. Because even if you get a big bonus from one assignment, it doesn't necessarily mean you will pass the class, right? Generally speaking, unless you define passing the class is to get really high score on one single assignment. That makes sense.
Yeah, it's a kind of contrived example. I'm like, what if the extra?
So I'll give you a more intuitive example. If you score, all of you know football, right? Even if you don't like football game, you know what football is. Even if you don't know what football is, you know how to decide who wins a football game, right? Or not? Who score higher, who wins the football game, right? How hard is that? Now, what's a sufficient condition? If you score more than 10 points, or if you score, okay, using US football, right? Let's talk about real football, right? You score more than 14 points. What that means, if you score more than 2 touchdowns than your opponent, you win the game. That's a sufficient condition, right? Must be. If you score 2 more touchdowns than your opponent, meaning you score 14 points more than your opponent, you win the game. You follow this? That's a sufficient condition. You follow this? Is that a necessary condition? Obviously not. Why I need to score 14 points more to win my opponent, to win the game? You only need to score 1 point more to win the game. So that's a sufficient condition, but not a necessary condition. Follow this? Yes? Okay. Is there an example where it's a necessary condition, but not a sufficient condition? So the example I just gave you will not work, right? Because it's only a sufficient condition, but not a necessary condition. Is there an example where it's a necessary condition, but not a sufficient condition?
Not related to the football example, but like if you said if it rained outside, the grass will be wet.
If it rain outside,
the grass will be wet.
The grass will be wet. Okay, very good. That's a sufficient condition, but you just reinforced what I said. That's a necessary condition, but not sufficient. That's a sufficient condition, but not necessary condition. If it rains outside, the grass will wet. But if the grass is wet, doesn't mean it must rain outside. So you just give yet another example where it is a sufficient condition, but not necessary. You follow what I said? But I'm looking for the other one. Let me give you an example. Right? There are tons of such examples. Having enough gas in your tank is a necessary condition to drive your car. But is that sufficient? Is that sufficient? If I take 2 wheels out of your car, give you a full tank of gas, can you drive your car? You can. You can. Give me your contact. If one day I open a company, I become business owner, I want to hire you as my assistant. That's a necessary condition, but not a sufficient condition. It has to be a necessary, but something has to be a necessary condition because without it, that statement cannot be true. Without any gas, you cannot drive your car. Even if it's perfectly functioning car, the car won't start without gas. But only having gas is not enough. So all of you, I hope this simple example should you have something to add? Go ahead.
Yeah, I'm not sure I understand back to the rain example. How is the grass being wet a sufficient condition for rain?
Let me. This direction is true, right? This is the if. If it rains, grass is wet. That's sufficient condition.
Right,
but it is necessary. Grass is wet doesn't mean it's rain, right? It could be a sprinkler, right? Why it has to rain for grass to be wet? Your grass can be wet for a lot of reasons. I just have my Coke spill over on the grass. That happens, right? No? By the way, I stopped drinking Coke, so I have my water spill over on grass. It took me 6 months to get rid of Coke. Okay? Do you follow this?
Yes, although I thought that
so you don't go, you can, this direction is always true, but this direction is not always true. Okay? If you still have puzzle on this, we can talk about this offline. Okay? Because grass is wet can be caused by many things. Rain is just one of the possible things causing grass to be wet. So it's a sufficient condition, but not necessary. Okay? So this is the if. This direction is only if. And in short, if you have both directions, that's if and only if. Okay? That's why this is if and only if. Okay? So all of you should be, crystal clear on this, right? Because these are not only useful for database course, right? This is not only useful for computer science stuff. It's useful for whatever you do in your life, right? If somebody offer you a contract, right? And you need to understand whether the condition in the contract is sufficient condition or necessary condition or both before you sign a contract. Okay? So what is this condition? We spent so much time on talking about this, right? These 3 letters. Now we understand what this 3 letter means. What is this particular condition? What is this particular condition? What is this particular condition? Well, the condition is actually fairly simple to state. X intersect Y. X and Y are 2 sets of attributes, right? So they're set. You can do intersection over them. If you intersect them, if this determines either X or Y, if either of this is true, then this is true. Then this is true. Okay. This means always equal, right? When I write 3 horizontal lines, that's not just equal, it means always equal. Meaning that for any instance you can come up with, this is always true. In other words, it's a lossless strong transition. Okay? So let's try to understand this using a specific example. Let's try to understand this using a specific example. Let's come back to the example we just had. My R in this example is A, B, C. My R1, which is my X, this is my X, is AB. My R2, which is Y, which is BC in this case. You always follow this? Yeah? What is my X intersect Y? What is my X intersect Y? My X intersect Y is AB, and that's simply equal to B. Yeah? Now you check, does B determines X, B determine Y, B determine Y. In other words, you check X intersect Y, determine X or determine Y, which is equivalent to say whether B determines AB or B determines BC. Is any of this true in this case? No, right? The only thing hold over this is A determine B. The only thing hold over this is C determine B. You have nothing to show B determine AB or B determine BC. So this is not true. But it's only if we just explain what is a necessary condition, right? Necessary condition says in order for this to be true, this must be true. That's the only if. The if is if this is true, this will be true. That's the necessary condition. This is the sufficient condition. Given that this is not true, which means that this cannot be true because it's a necessary condition. Henceforth, we draw the conclusion that this is not a lossily strong decomposition. Henceforth, it's not surprising to see that joining them back actually do not give you the original relation because it's guided by this principle. It doesn't satisfy this necessary condition. It doesn't satisfy this necessary condition. In other words, transfer to plain English, to use a metaphor, it is surprising to see you cannot start your car when you have no gas at all in your tank. Don't run around like you found a treasure, right? That's not surprising at all. It's a necessary condition to start your car. Okay? But if you cannot start your car with a full tank of gas, you have 4 wheels, your engine was running just fine, yes, then you have a reason to go around and to be surprised. But not if you have no gas in your tank. Don't be surprised. That's a necessary condition. If you cannot start your car, that's typically, that's very typical. It's completely normal. Right? Nothing is wrong. Right? Okay, so that's a necessary condition. Now, I show you how to apply the check this way, right? This result is also useful to go this direction, meaning that given R, and of course the functional dependency over R, I can apply this to ensure that I always have a lossless strong decomposition. I always have a lossless strong decomposition. Okay, let's check how we do that. We're going to use the same example here. Okay. So I'm going to apply the if direction, the necessary condition direction. Sorry, the sufficient condition direction. Meaning that when this is true, then the results are guaranteed to be lossless strong decomposition. Okay? What's my F? My F in this case is, right? Keep that in mind. Well, I'm going to decompose this into, follow the slides. I think I said AC, double check. Oh, BC, okay, AC and BC, okay? Okay, that's what I do. What is my X? My X is this. What's my Y? My Y is this. All of you follow this? So far so good? Now, I guarantee you that this is lossless strong decomposition. Why? Can someone tell me why this is guaranteed to be lossless strong?
Because their union is going to be C and C.
The union, no, yeah, not the union, the intersection.
Sorry. Their intersection is going to be
C, yes, and?
And C determines CB or BC.
C determines BC, because C determines B, C determines C, so C determines BC. Which means X intersect Y determines Y. Remember, the condition is all, right? I don't need to have both, I only need to have one of them. C does not determine AC, but that's okay because it's OR condition. If, right? It's like if range bracket black. Okay? So this guaranteed to be a lossless strong decomposition. And if you still don't believe me, you can check this using this one instance and you get it back. If people can still make argument, wait a minute, you just show this over a single instance, how can you convince me this works all the time? Fine, take your time. Try all possible instances. No matter how long you try, because of this, I guarantee you that they always join back to the original instance. Okay? Of course, the catch in our argument is we never formally prove this. We never prove this. Right? We never prove this. But somebody else has proved this already for us, so we don't have to worry about that. Of course, we can go into the details of that proof, but that's not trivial at all. So I'm not going to bother you with that details, but just take this as a fact. But this does raise an interesting, this simple example raises an interesting observation, which is given a decomposition, I can check whether it's lossless or not. Right? Applying this rule, I can easily check if it is lossless or it is lossless. I can easily check this. But how do I get to this place in the first place? How do I go from here to here in the first place? On a simple example like this, it's fairly easy to make some quick observation. You say, okay, if you decompose this into AC and BC, you get this common attribute C that determines one of them. That's fine. But if you have a schema that have multiple attributes, very complex functional dependencies, how do you do this? How do you do this effectively? Is there a mechanism you can follow to do this without just making some ad hoc observations all the time? Do you follow me? Yeah? So I'm gonna show you what is that. How do we do this decomposition, right? Let's erase this and see how we derive this in the first place. A useful result is that given this, a useful result is, so if we call this a theorem, this will be a lemma. A lemma is typically something that's trivial to show once you have a theorem in place, dependent on that theorem. Okay, that's what a lemma is. A useful lemma is if you have and okay, if these two conditions are true, then you can always decompose into and this is guaranteed to be lossless. Okay, it's guaranteed to be lossless. W and Z are two, again, just subset of attributes from R. Subset of attributes from R. I will pause for a while and let you read this result and understand this result. Okay, and I'm gonna do two things after this. One is I'm going to show you an example of using this result. I'm going to show you how to use this result in practice. Secondly, I'm going to prove this for you. I'm going to prove this using this theorem to prove this for you. Okay? All of you follow that? Let's do the first, which is how do we apply this in practice? Okay, let's come back here. Come back here. I can take this as my W determinant D, in which my W is A, my Z is B. You follow this? W and Z are just symbols representing a set of attributes from R. So it can be A, it can be B, it can be anything actually from R. In this case, I just use W as A and Z as B. And I check if W intersect Z, which is A intersect B, is it equal to empty set? Yes. The answer is yes. So the two conditions are true. Check, check. Now I can apply this result. I can apply this, meaning that I can decompose R into R is A, B, C, Z is B, and W is A. Right? So what I got? I got A, C, and what's the other one? What's the other one? What's the other one? Yeah. Okay. And this guaranteed to be lossless by this time. So now we get something interesting, right? Earlier, using this result directly, we can only check if a given decomposition is lossless or not. Now using this result, we got a functional way of decomposing a given schema into lossless drawing decomposition. That's more useful result. Right? Do you follow what I'm saying? It's kind of like somebody tell you, I have a wonderful method that you can apply to test if something is a dog or cat. Wonderful. Oh, you don't, okay, by the way, I was like you, when I first heard this question, I was puzzled by why that's hard. There are certain cases this is really hard. Google cat, dog. I don't know what's the keyword in Google, but there's a particular cat that looks just like a dog. And this is one of the AI challenge, by the way, artificial intelligence challenge. Okay? So what we said just now is you have a wonderful method to check whether something is a dog or cat. Now I'm giving you something even better, which is, what if I, in order to check, I have to have something to begin with, right? What I'm giving you now is a method to guarantee to produce a dog, but not a cat. That make sense? Okay? That being said, you have a question. Go ahead.
Yes. So if it's something more complex, like you mentioned previously, would it mean we would have to break it down first before using that?
What do you are jumping ahead. You mean if this is not true, if this condition is not true?
I'm saying the condition, if it doesn't hold, but we need to break it down more to actually get to this condition.
What doesn't hold? This doesn't hold or this doesn't hold? Oh. What, to be, I want to quantify your question a little bit, right? What do you mean if it doesn't hold? Which doesn't hold?
Since we need both conditions, either.
Yeah, we need both conditions. You're asking what if one of them is not true, right? I will talk about that later on. Okay. Okay? But before I do this, next I'm going to prove this for you, right? But before I do that, is there another decomposition that's also lossless? In this case, is there another decomposition that's also lossless? So this is one decomposition, right? Is there another decomposition that's also lossless? Well, you can, if you can do this over A determined B, you can also do this over C determined B. Right? So you simply say this is UW, this is my V, and W determines V, and C intercept B is also empty set. So this is true as well. Now, in my case, I will ask one of you to show me this. What's R minus Z, and what's W? Can someone tell me? Well, somebody else. You've been answering too many questions. Somebody else? Somebody else? Yeah, go ahead. CV here, and what's here? Okay. Excellent. R is ABC, right? Z is B, so you take B out of ABC, you get AC, obviously. And you merge W and Z together, that's simply BC. And this guaranteed to be lossless is wrong. Why? Well, you check the intersection of them, what do you get? You got C, which determines BC. But this result is done. Okay? You follow this? Okay, now, so that's how we apply this result in practice to do decomposition. By the way, that's what commercial engine is doing, right? When you go to a commercial engine, you supply a set of schemas, you supply the function dimensionally, hold over them, you ask the engine to check whether they are B, C, and F. If not, do decomposition. That one button click essentially invoke all of this stuff. You follow this? Of course, I have to go back to answer your question. What if this condition doesn't hold, and I cannot do any decomposition to begin with? What do I do? There are ways to fix that, which I will talk about in a minute. Now, before I talk about that more complex case, more general case, I want to prove this for you, that given this theorem, you can actually show this lemma. That's what I'm going to show next. Okay? I'm going to prove this. I'm not proving the theorem itself. This is really hard to show, actually. But going from here, given this, to show this lemma is actually trivial. It's not that hard, which is what I'm going to do next. Okay? You follow this? All of you? The observation is, you have R, and you decompose this into right? You decompose this into this two. Now, what's R1 intersect with R2? Can someone tell me? That's nothing else but R minus D intersect with WD. And what is this? What is this? Can someone tell me what it is? W. W. Excellent. Can you justify your answer a little bit?
So R minus C, R is everywhere. So taking away C, you still have W and R minus C. And then W is related to WC.
Your argument is perfect, except one minor defect, which is you do need that condition. The intersection of the two is empty. Why? Let me demonstrate that, why this condition is critical. I hope all of you follow what he said. What he said is almost perfect, except that there's a corner case he didn't consider that required this particular condition in order for the result to be done. Okay. Draw out of space. I can erase this because this is on this slide. Anyway, so the what? What's R? R is nothing else but a set of attributes. Right? And what's R? You can think about R as I definitely have W, I definitely have V, right? And I may have something else. The something else, I'm going to represent this using, I don't know, like some symbol called M. It's a set of attributes. I don't care. Does that make sense? Yeah? And given that the intersection of the two is empty, I know there are no overlapping between these two parts. I'm using this condition right here. You follow this? Okay, if you don't follow this, let me give you. If somebody asks you draw a map of the entire world, like world map, all the countries and all that stuff, how do you draw this map? If you are from US, that's easy. I will draw this map for you. There's USA, there's Canada, and there is the rest. Done. That's a map of the world. What's wrong with that? No? You know, that's the impression I have on US when I first landed in this country 20 years ago, right? Like there's US, there's Canada, there's the rest. Okay, that's your W, that's your Z, and that's your M. Of course, this may not be a good example because some people may argue W intersect Z. Wait a minute, it's not empty, right? That's a joke if you don't get it. But some people argue Canada is the 51st state, right? So intersection may not be empty, right? So let's say we take off W and intersection of W is indeed empty, right? That's what we have here. Do you follow this? I hope now you follow this, right? Okay. Now, what's R minus Z? It's simply W and M. That's something else. What's WD? What's WD? It's just WD. And the intersection of them is what? Intersection that must be equal to W as the argument. Yes? You may wonder, okay, fine, what's the big deal of intersection being W? Well, the point is W determines WZ. Which means, in other words, R1 intersect R2 determines R2, and using these results, I'm done. The intersection of the two determine one of them, the result guaranteed to be loss disjunct. And of proof. And this holds for whatever schema R you have. Okay? Now let's come back to the defect I pointed out in his argument. You still don't understand this, right? I mean, take a political incorrect view of this, right? WM is US and all the other countries. WZ is US and Canada. As long as you're US, you're fine. You're done. You determine everything else. This is a politically incorrect thing to say, but you know that's the order we're in today, right? You follow this? Yeah? Okay. All right. What if this is not true? That's the defect I pointed out in your argument, right? If this is not true, what happens? What happens is you cannot draw a nice partition between W and D anymore. That make sense? You have to, this has to be represented using some more symbols, such as W prime, D prime, and some common part C, where this gives you W and this gives you D. Because the intersection of them is not empty, right? Yes? You follow me? All of you? Yes or no? In particular, I let it equal to C, right? The intersection equal to C, that's not empty. So that's this part. So this together is W, this together is D. Now what's your R minus D? What's your R minus D? Huh? You don't get Wm, you get W prime M, which is the subset of W. What's WMD? That's still WD. There's nothing, no trick over there. Now what's the intersection of the two? What do you got? Someone tell me? What's the intersection of the two? You got W back? You got W back. You are intersecting this with this. What do you got? Do you got W? What do you got? You got W prime. You got W prime. In some sense, you don't get all US, you got some part of US. Does this determine WD? Does it determine WD? Obviously not. Obviously not. You follow this? Henceforth, this condition is critical. This condition is critical. Okay? This condition is critical. Okay? Now, last trick. Okay? There are enough tricks today, but there is one more trick I wanna show you. Okay? It's kind of related to his argument, his question. What if this is not empty? Like what we have here. And this equal to, let's say this equal to something called C. The common, why I use letter C? Because that stands for common part. Okay? Common part. How do I do my decomposition so that the decomposition is lossless? You follow the question? All of you follow this question. Right? Do all of you follow the question? Okay, good. How to solve this problem? How to solve this problem? Okay, let's look at this together, okay? I'm gonna go back to this example. That's exactly what we have. And this is my W. My W is essentially W prime and C. My Z is C and Z prime. Henceforth, the intersection of the two is the common part C, right? That's what I have, right? You follow this? How do I decompose this such that the resulting decomposition is lossless? The key observation is I do have W determines Z, right? I have this. W determines Z can be written as, it's the same as this, right? I'm doing nothing but rewriting what you're telling me. Let's say in a trade negotiation, right? We're talking about trade negotiation nowadays. Let's say, again, always incorrect statement, right? In the negotiation, U.S. dominates the negotiation with the trade negotiation with Canada. So U.S. determines Canada's trade policy. Let's assume that's the case. Don't come back and hold me against that, okay? I'm using an artificial example. Okay? Now what I'm saying is 49 states plus California determine the trade policy of Canada plus California. Suppose, again, artificial example, California is shared by US and Canada. That's what I'm doing, right? I'm just changing the symbols, but I'm stating the same thing. You follow this? Okay, once you get this part, the remaining is trivial. Because I have C on both ends, you follow this? What do I get? Okay, this is another tricky part. Do you have this? Can you job C on both ends? You get this. Huh? No, that's what we said. It's not a arithmetic operation. You can job common attribute from both ends. So this is not true. But you can job attribute from the right hand side. You do get this. You do get this. You follow this? And translate back, this is nothing else but W determines Z prime. Now it's almost trivial, right? If W determines Z, then W must determine a subset of Z. And the even more important observation is now we have W intersect Z prime is empty set. You're intersecting this part with this part. Of course, it's going to be empty set by our construction. Now what? Trivial. Now you simply view Z prime as Z, apply this theorem here now. In other words, what's your decomposition? You decompose into R minus Z prime and WZ prime. What's Z prime? Z prime is defined as this. Okay? This is nothing else but this common part C. Okay? I'm going to leave this, by the way, as a homework assignment for you guys to figure out. Do all of you follow this? Somewhat, I guess. Right? Which means you need to review this. Okay. So now I think we're almost ready to wrap up this whole discussion on normal form and function. I need another maybe 20 minutes to do so, which I'm not going to have time to do that today. But we'll use the remaining 5 minutes to introduce another key observation. Then coming back on Monday, I will wrap up everything. Then we're done. Okay? Move to something. Okay? Move to something else. Okay. So the earlier example, this decomposition doesn't work because the intersection AB and CB is B. And B does not determine AB and B does not determine BC. So the intersection does not determine any one of the two resulting relations. Henceforth, it cannot be a lossless joint decomposition. Why? Because it is a necessary condition. Not only is it sufficient, but also a necessary condition. So we know for sure this is not lossless. And so we try another approach. We decompose into AC and BC. In this case, we guarantee to have lossless joint decomposition. Why? The intersection of them equal to attribute C, and C determine BC. So you can show that you decompose into X and Y. X intersect Y determine one of either X or Y. In this case, determines Y. We're done. So guarantee this to be lossless joint decomposition. This is when applying this result in action. Applying not this result, the earlier result when the intersection is equal to empty. Right? Apply that in action. In fact, this is a more general result, right? If you substitute C into an empty set, what do you get? You basically get this is empty, so Z prime just equal to Z. So using this result, the empty set intersection is just a special case of this result. It derives that. Okay? Now, by the way, this is a useful trick to remember, right? When you make a statement, when you make a general claim, if you don't know how to show your claim is true, at least check some extreme case. Give you an example. Bama is going to beat all the teams. You make a bold claim like that. You don't know how to prove this. At least sample a few strong teams and see whether Bama beats them. If Bama beats them, it doesn't mean Bama beats all the teams, but at least it means that you have more confidence in your claim. Right? So check some corner cases. That's one thing. Okay? Special cases, whether it holds. Now, there's another issue with decomposition, though. We talk about lossless John decomposition so far. Right? This entire lecture is devoted to that. But there's another challenge while decomposing a given relation, which is, I think she made an excellent observation on Monday. The fact that, okay, if you decompose into this, AC and BC, lossless John is guaranteed. And you joining them back always gives you the original relation. However, there's another problem with this decomposition. I started with, and also two functional dependencies. I end up with where my F1 and F2, F1 is the set of functions with the hold with regard to R1, F2 is the set of functions with the hold over R2, is here is empty set. There's nothing hold over here. And here is, right? You follow this? On this end, I'm okay. I join them back, I guarantee to have R. That's because the intersection is C, and C determines BC. So this is guaranteed. So on this end, I'm okay. Check. Right? That's the entire lecture is about. But on this end, functional dependency, you don't join them, right? There's no operation join over functional dependency. You union them. You union them, what do you get? You get C determine B. Unfortunately, this is not equal to the original set of functional dependency you start with. This A determine B is lost. And this is not okay if you think about it, right? If you tell your boss, fantastic, I find a decomposition that gives all the records back to you. You don't have to worry about it. However, an important constraint is lost. For example, A determine B, maybe rating determine weight. Your boss will not be happy with that. If you tell him or her a decomposition like this. Do you follow this? And this particular observation brings up the next topic, which we will discuss on Monday, but I want to introduce the concept, which is called dependency preserving decomposition. Naturally, if this equal to the original set of functional dependencies you have, then that's called a dependency preserving decomposition. If it's not, then it's not a dependency preserving decomposition. Now we understand the ultimate goal of normalization. The ultimate objective is to get lossless John and dependency preserving decomposition. To do both at the same time. Question is, how do we do that? I will continue on Monday.
John, do we have like a number
I don't know if it's out right now, but you will have, you just need a color tree.
Yeah, no worries. Yeah.
See the test. I can't take it. You have to talk to you don't have both? No. Point in the back. context. I hate that context.